Okay, hello everyone. Nice to have you for our vLLM office hours number 33. My name is Sasha Zelanovic, and I'm one of the organizer here and one of the co-hosts as well. I wanted to take this chance and just quickly ask about people that this is their first time. So how many first timers do we have? Is anybody here for the first time at the vLLM office hours today? Maybe at chat, do a little chat, or maybe raise your hand, send a reaction. Any first timers? All right. Hey, Oscar, welcome. Nice to have you. I'm sure that we probably have a little bit more than just Oscar. Hey, yeah, we have more. That's awesome. Good to see you guys. So welcome to our vLLM office hours. This is a bi-weekly program. It runs every other Thursday at the same exact time. It's a very safe space for the community to obviously learn and hear about the new vLLM project updates. We bring on special topics every week or every other week. And if you have any questions, if you have any feedback, this is a complete safe place for the vLLM community to collaborate and project the project forward. So thank you very much. There's a lot of repeat attendees here, so no question is too foreign for us. Please keep asking. So today I'm really excited about our session today. So first of all, we have Michael Goin here. Michael has been here with me for every single vLLM office hours yet to miss one. So thanks for the commitment, man. Michael is a software engineer at Red Hat, also one of the early vLLM project committers. So there is probably not much that Michael doesn't know about vLLM. So if you have any questions or feedback, great person to know. And then Thomas, welcome Thomas. I believe you're calling from Switzerland, correct, Thomas? Yeah, Thomas is working at IBM Research. We've done several things together with Thomas in the past, including present at the New York City meetup. More things. Thomas is also a vLLM committer, very focused on hybrid model and hybrid model support in vLLM. Very timely topic with all of the hybrid model hype with Goin and all the other things that are happening. So really excited to do this special topic today. Michael, can you please go to the next slide? So, as I mentioned, we do these vLLM office hours every 2 weeks. Today we'll be talking about hybrid models and specifically sharing the Mamba examples. And then in 2 weeks, on October 9th, we'll be talking about the AI-powered vLLM semantic router. Super cool project, by the way. So it was contributed to vLLM a month ago at this point, maybe a little bit less. In the first few weeks, it received nearly 1,500 GitHub stars. So there's definitely a lot of excitement around this topic. If you just Google AI-powered vLLM semantic router, you'll get some info. We wrote a blog about it. You'll get a direct link to the GitHub repo. But next, or in 2 weeks, we'll be doing a deep dive with one of the key project people there. So please come. Yeah, thanks, Michael, for sharing that. Please come learn more. Give us, feedback and see how that works. That's awesome. We are recording this, as you guys probably know already. It will be live on YouTube. Recording will be on YouTube right after this call. So feel free to get that and share it with your colleagues. Michael, what's going on, man? What is new in vLLM in the last 2 weeks since we last spoke?
Yeah. Hey, Sasha. Hey, everyone. Thanks for the warm welcome back. Yeah, we've had a very busy past 2 weeks. I know at the last office hours, we didn't have a release to talk about because we are working very heavily on the 0.10.2. So it's a pretty big release. We'll cover a lot in what's new there. And we have lots of model releases and blogs and stuff to share with you this time. So we'll walk through those and what's been happening in the vLLM community. Yeah, so let's first talk about some virtual events that we have coming up. Yeah, Red Hat is running some basically parallel paths, like both in both in terms of learning about Red Hat AI and also a specific day of learning to learn about how to use AI from a lot of the experts here at Red Hat and IBM. Obviously, a lot of vLLM. But a lot of other things in terms of how to start, using modern AI tools a lot more securely and effectively. So yeah, these are going to be live virtual events, and we'll have lots of question and answering available. So yeah, check it out, sign up, and see if you can learn something for your business or your projects from that.
Give me one more chance at this to hype a little bit more up.
Sure.
So the AI Day of Learning, we're super excited about this one. It's 3 months in the making. We have 4 tracks, 12 sessions, 17 different speakers. Sounds like a lot, but it's a sub 2-hour event. It will all be recorded. We'll write blogs. Please join us, ask questions. Typically in these office hours, we focus on the fast and efficient inference with vLLM, but we'll also be digging deep into model customization. So how do you actually align your enterprise data to your models, how to build agents, so agentic AI, and also how to scale across the hybrid cloud. And then if you want to know what's really new from the Red Hat product perspective, on the left-hand side, what's new and what's next, we'll share what we're working on, what do we plan to work on. We would honestly love everybody here to scan these QR codes right now and join us. Even if you cannot make those specific times, just get in that stream and we'll make sure to send you the recordings and the blogs. Anyways, Michael, back to you.
Yeah, thanks a lot for the color. Appreciate it, Sasha. So first, hopefully many of you are familiar with vLLM at this point. We want to sort of cut back on the amount of repeat content that we do. But just to start you off, vLLM is an open source standard for model serving, specifically large language models, but also multimodal models, inputs and outputs. Really in terms of anything that's coming out of the latest model labs. In terms of state-of-the-art models, we want to support those and let them have a home in vLLM, especially since vLLM has a broad swath of hardware vendors that support and glue themselves to the software interface of the project. It's a really key interface for the open source AI community, so you can easily deploy DeepSeek or Llama 4 or GPT-OSS across your possibly millions of dollars of expensive hardware that you've purchased. It started off as a research paper, a very simple project, but has had obviously a huge amount of community growth. You can see from the start history on GitHub, but of course many different academic institutions and research institutions and enterprise companies all collaborating on it with over 1,500 contributors. Yeah, hope you can be one yourself if you haven't contributed yet. So first thing I want to kick off with what's new these past 2 weeks is a blog from the PyTorch team at Meta. They have been running distributed inference internally, obviously, for over a year now with their internal stack, and they've been turning to use vLLM a lot more. And they sort of walk through how vLLM has replaced their custom inference system for disaggregated serving for Llama, and share some reports and some findings on the benefits of disaggregated serving versus non-disaggregated. Here we're talking about specifically disaggregating prefill and decode operations and splitting these up with different levels of parallelism or replication. So yeah, recommend checking it out for a bit of a deep dive, but also a good introduction to how disaggregated inference works and the benefits of it. Next, definitely want to give a big shout out to the Goin team at Monkey Lab in Alibaba. They hope you should definitely know them by now, as their model releases have been great over the past years. But yeah, particularly this past week or so, they've been killing it with too many model releases for everyone to keep up with. Here we have the 3 major ones: Qwen 3 Next, which is supported in 0.10.2, and features a very efficient hybrid attention architecture. So very thankful for Thomas's participation in that support in vLLM. And then there's Qwen 3 Omni, which is a really impressive step towards it's probably the best open source example we have of a large scale usable omni modality large language model, meaning multimodal inputs but also multimodal outputs. So we definitely support the text capabilities of it. We're still working on multimodal output support and expanding for all the complex modalities for that, both image and audio. Yeah, it's a pretty cool architecture, and we're excited to see usable models for omnimodality. And then, of course, most recently, Qwen 3 VL came out, which is a vision language model extension on top of the Qwen 3 release, which has been highly anticipated. And yeah, it seems like a beast in terms of now we have basically it's a over 200 parameter mixture of expert model with very strong vision language understanding. So yeah. This has been really fun to support, and yeah, super great model releases. Next thing I want to share is actually like a paper and blog shared by the How AI Lab. They shared a new form of kind of speculative decoding that's specifically for reasoning models, thinking models, that essentially goes through the idea of using a smaller draft model specifically for the reasoning or the thinking part of inference, and using this to generate multiple reasoning traces in parallel, and yeah, just trying to skip over more of the reasoning steps and get more efficiency out of there by specifically focusing on the reasoning step and the kind of peculiarities and repeated patterns that happen in there, versus just trying to do like a general speculative decoding method like ngram or Eagle, like we currently sort of recommend. They did all their experiments on top of vLLM and made it all available as a fork. So it hasn't integrated in upstream vLLM yet, but yeah, we're interested to start looking at it. And yeah, if you're interested to start looking at it, we'd be happy to shepherd you. It's a pretty cool project, and definitely recommend reading the blog and the paper. Another model release to cover is the latest iteration of DeepSeek's v3.1, the Terminus model, which is specifically capable in code editing and agentic use cases. This is pretty standard. It's basically the same architecture as 3.1, so it's just a clear substitution there. But it gives us an opportunity to talk about one of the latest features, which made it in 0.10.2, which is decode context parallel, which was added actually by the Kimi Moonshot team. So they released like Kimi K2, which is also based off DeepSeek's architecture, but scaling out up to a trillion parameters. So they really needed something like this. So if you've ever used DeepSeek with tensor parallelism, you maybe don't know, but in that case, because we only have one KV head due to MLA, we need to replicate the KV cache across all of the TP ranks. And so decode context parallel works very well in this case, because now we can start to not just replicate the KV cache on every GPU, but start to shard the different bits of KV cache for each layer across all the GPUs. So in the case where we're hosting DeepSeek v3 on, say, 8 H200s with tensor parallelism 8, we can enable DCP8 and get 8 times larger KV cache. So obviously a lot more context, but also a lot more throughput. Here, where I kind of highlighted in the box, we have 8 times the KV cache, and around 2 to 3x throughput gain is what we measured in high throughput scenarios. So yeah, pretty powerful argument in just like 4 characters or so to 8x your KV cache is pretty cool. And this works with older DeepSeek models as well. Anything that uses MLA, and we're working on expanding this to non-MLA attentions as well. And a bonus, hopefully if you've seen on the mainstream news, the DeepSeek R1 paper finally got published in Nature, maybe like 8 months late or so, but that's traditional journals and academia. So congratulations to the great work from that team. Obviously, GRPO has been kicked off a ton of the reasoning advancements in open source AI. And of course, we're going to mention that there's a mention of vLLM in Nature now, because they mentioned how they managed and used vLLM workers during their RLHF training process. So yeah, cool to see vLLM in production and also in state-of-the-art research. So yeah, that's what I wanted to cover there. Now let's kick off into what's new in the latest release of vLLM. This was a pretty chunky release, as I already mentioned, over 700 commits from 266 contributors, with 97 of those contributors new. We cut a new release every 2 weeks, so that's a lot of new contributors to have in 2 weeks. So some things I want to cover in terms of model support. Obviously, Qwen 3 Next was a really important and challenging model to support. I'll cover some of the new kernels that were needed for that, which is cool. Also, Intern VL 3.5, another Chinese lab that's has a very capable multimodal model. This one has pretty interesting video encoding optimizations. And finally, we've added Whisper to vLLM v1, closing off one of the main blockers we had from deprecating v0. So now we have support for encoder-decoder, model architectures, which is great. Another thing I want to mention is, a lot of added LoRa support to models from previous releases. And we fixed the big issue where the startup time for launching models with LoRa was significantly longer than without LoRa. And we basically reduced this to 0 now. So there's effectively no startup cost. So if you use LoRa in production, you're probably going to be very thankful for that. Lots of various other improvements for model support. But I'll go ahead and move on to v0 deprecation. So this is basically the last release before our next release, which is 0.11, which is when we hope to pretty much fully remove v0. But in this release, we removed some hardware backends, a lot of the v0 encoder support, and a lot of attention backends as well, which is pretty good to see. And we also removed the features from v1 that we've dedicated to not supporting, like prompt token IDs and some rarely used LoRa features, like mixing tokenizers and things like that no one was really asking for. Next, in terms of improvements to the engine core, another key thing for v1 compatibility is we support GPUs older than 8.0 compute capability. So this means your Tesla, your NVIDIA T4 GPUs, and even V100s, I think, will be supported now, although unfortunately the V100s are going to be dropped in the next version of PyTorch. So that's a really good improvement. Also relevant for hybrid models here, we got full CUDA graph support for Mamba attention, which really helps out with the CPU overheads we found there. Lots of improvements to weight loading. We've been trying to optimize the performance of that quite a bit. A really key thing is multi-threaded weight loading is now available. We now have a sort of weight loading config where you can define these things. Hopefully, we hope to enable this by default, but currently it's locked behind this flag. So if you want to learn more about messing around with these things and see if it works for you, highly recommend checking out that PR. Another key thing is a much requested feature from researchers is supporting returning all the prompt log probs in an efficient way that doesn't crash the server. So that's well supported now. And as I mentioned before, decode context parallel from the Moonshot team landed for MLA. There's been a lot of work and development from the hardware side on NVIDIA Blackwell GPUs. We're still working very closely with NVIDIA on getting mini kernels from the FlashInfer library into vLLM. So this involves a lot of Cutlass-based MOEs and also TRT-LLM, Cuban-based MOEs, and we also pushed for GPT-OSS, YDP or DPEP support for throughput scenarios. Lots of other optimizations for MOE models. Expect to see more of those in the coming releases. We're really grinding down and staring at the profiler for large MOE models like DeepSeek and GPT-OSS as we find more of these, as we run cluster scale wide EP inference. Yeah, one key kernel that was added, that was necessary for Quantum Next, is this flash linear attention. It's a pretty cool idea. So yeah, if you're interested in sort of state-of-the-art hybrid architectures, definitely recommend reading up more about that. And yeah, we also added sort of the first performant kernel for W4A8 quantization. So int4 weights and FP8 activations for mixed quantization. And another really key performance improvement, if you've used the async scheduling option, is we've fully overlapped the model execution with the scheduler in V1. So this was sort of a key performance improvement there. And yeah, we're really hoping in the next release or two to enable the async scheduler on by default, which should really help in very high throughput scenarios. Yeah, please give it a try if you haven't. Finally, the last three things here is one thing I want to mention is the compressed tensors transform support for applying Hadamard transforms before and after linear layers. This is really critical for recovering accuracy for these very aggressive modern quantization methods like NVFP4 and MXFP4 are going to even lower bit precisions. So yeah, we have some initial kernels and checkpoint integration support for this. So yeah, expect to see some papers and hopefully some models that at low precisions that recover accuracy better due to these transforms. Yeah, and then in terms of dependencies, this was a pretty hefty one because we finally upgraded PyTorch, a minor version to 2.8. We're also looking forward to update to PyTorch 2.9 in the middle of October, so be aware of that. This also means that we support CUDA 12.9 wheels as well. Nice tidbit there. And then various optimizations and improvements on the API and front end. Probably the one I'll just mention here is the response API improvements. Particularly, helping models like GPT-OSS to be usable in more scenarios, especially for tool calling without using the Harmony style response format. Yeah, that's all I wanted to cover here. Obviously, as I mentioned, a lot. The last few things I want to cover is, this is the first release that supports CUDA ARM specifically. Or rather officially. So now on PyPy and on the official, Docker Hub image for vLLM, we support CUDA ARM, hopefully as magically as possible. So if you're on GB200 or GH200 with those Grace CPUs, vLLM is a pip install away. No longer need to build yourself from source, which is great. And a self plug for something I landed this week is enabling full CUDA graphs on by default, which is a really big optimization that we've wanted to do for a while in vLLM v1 that is really going to help low latency optimized scenarios, especially as we have more and more of these efficient MOEs that really don't activate that many weights, even as you run decent sized batches. So yeah, should expect a large improvement here in the next release.
Michael, so, you said so many great things. You're an hourly active user of vLLM, maybe even more often. Like, can you single out one thing? What's your favorite thing that you mentioned?
Definitely the full CUDA graphs on by default. I felt like this is a bit of a crime that we haven't had it on for so long. It doesn't really affect high throughput scenarios. But for those users that are running like really small models on really big GPUs, like H100s and B200s, if you're running like just a few billion parameters of a model, not having CUDA graphs on the attention operation, can really add up. So yeah, this is a really key thing that is going to, fix a key deficiency vLLM has had for really low latency sensitive, say you're just optimizing for like really short requests and you need end-to-end time to be like 100 milliseconds. That this is like really important for like coding agents and like coding assistants, where you need to very quickly predict what the user is gonna type before the user types it. So we're really excited about it.
Thanks, man. While you're passing it over to Thomas to present, welcome, Thomas. There was a question from Valentin. He was asking, do we know if decode context parallel shards KV cache across nodes?
Yeah, that's a good question. I'm not actually, I mean, yes, it should, at the moment, I believe it only works with tensor parallelism. And like, we usually don't recommend tensor parallelism across nodes. You probably want to do some pipeline parallelism, or just do expert parallelism and data parallelism, full data parallelism for the attention. So yeah, but I don't see why it wouldn't work if you just like say you're doing TP16 across two H200 nodes with InfiniBand. Yeah, it'll just work.
If Mooncake is part of it, it might. So yeah, that's cool.
Yeah. We still need to tune it and fix some things. It's more of a throughput optimization, but yeah, it's really cool. Okay, I'll hand it off to Thomas. Thanks.
Hey, thanks, Michael. Hey, good afternoon, good morning, good evening, everyone. As you can see, it's nighttime for me. This is my first time talking on the vLLM office hours, so I'm super excited to be here. I'm going to talk today about the work that we've been doing in the community to enable hybrid models as first-class citizens within vLLM, and I will explain what we mean by that. So yeah, the agenda for this talk is I'm going to start with kind of overview of what is Mamba, Mamba 2, linear attention. You may have heard some of these terms actually in the first part from Michael. Yeah, it can be very confusing. I want to try and kind of explain how these things are related. Then I'll talk about what are hybrid models, give a kind of overview of all the different models that are supported now in vLLM v1, what's similar, what's different. And then I'll talk about how hybrid models were initially supported in v0. It was kind of a hack, how we got them to work. And then I'll explain the work we've been doing to kind of gradually get them supported properly in v1. And actually, yesterday, or a couple of days ago, we stripped out the v0 support in main. So these models are now gone in v0. Finally, I'm going to show some benchmark performance, some performance benchmarks against v0, against v1. I'm also going to show the effect of full coup de grace for some of these models. Michael mentioned that already. As you will see, full coup de grace can really help for hybrid models too, especially when they use MOE layers. So yeah, just kind of motivating why hybrid models are interesting. Like, why do we see more and more hybrid models coming out? It all has to do with kind of the theoretical limitations of attention. So of course, everyone on this call, I'm sure, is convinced that attention is really, really good at modeling language. And in vLLM and its dependencies like flash infer, flash attention, we have loads of clever implementations and optimizations for doing attention on modern GPUs. Like Page KV cache was one of the original vLLM innovations. Then we've got like online tile softmax from flash attention, kernels that use tensor cores, the tensor memory accelerator, all different kinds of quantization. So there's a huge amount of work in that area. However, there are still some more fundamental issues with attention, right? And the two things I'd like to mention are that as we go to longer along sequence lengths, our KV cache will grow linearly. So every time we generate a new token, we append to our KV cache. So for really long sequences, we start using a lot of GPU memory. The other kind of fundamental limitation that is hard to overcome is that the prefill time, like the TTFT, is quadratic in the prompt length. So as we go to prompts of 128K, 1 million, the time to actually prefill the prompt can really blow up. So yeah, I just put the kind of famous equation for attention here because I'm going to link back to it in a couple of slides. So yeah, if you're not familiar, attention is basically like two matrix multiplications with this softmax in the middle. So first you multiply Q and K, T, K transpose, then you apply the softmax, then you multiply that all by V. That's kind of the core thing we need to understand about attention for this presentation. So like before I kind of go into what is Mamba, like why do we even care about long sequences? There are a bunch of different use cases that come out today where we see longer and longer sequences getting generated. One very common one is RAG pattern, right, where you have some user query, you retrieve a bunch of documents from your vector database and insert them into your prompts. And depending on how many documents retrieved, the prompts can get really long. Another common pattern is agentic workloads, where maybe we have a multi-turn interaction with the model, where we ask the model to generate something, maybe some code, and we go and call a tool to execute that code. We get some response, we go back to the model, and this process could repeat. Again, this is one where we can build up really long sequences. And finally, yeah, like thinking or reasoning patterns where we ask the model to think slowly, think through the problem step by step, to reason, where we may like insert some thinking or reasoning steps. Again, this leads to very long sequences getting generated with the model. So yeah, hybrid models really is all about how can we scale language modeling to long sequences without ruining the performance. So this is kind of the where I'm going to begin with state space models like Mamba. So this is actually a precursor to Mamba called S4. And in this paper, they defined an SSM as a map between an input sequence X of length T in this figure to an output sequence Y. So just think of it like a map from sequence to sequence. And the way that the structure of this mapping, S4, is shown here. I'm not going to go in all the details here, but what you need to understand is this is like a recursion, like with T steps. So for every, like the length of the sequence, we have T iterations. In each iteration, we take one of the inputs, multiply it by some vector B, and then we multiply this H vector, which is our state, by this matrix A. That's our kind of state update step. And then to get the output, we multiply the state H by some matrix C. So as you will see, like this matrix A has a very special structure, and how it's structured affects a lot how well we can implement these algorithms. But already from this description, you can already see that compared to attention, this algorithm is linear in the sequence length. So you have T steps, you don't have T squared work to do no matter how long the sequence gets. And the other thing that's very interesting is that the state vector H has its dimensionality n, which doesn't depend on T in any way, right? So this is like a constant size. It doesn't grow as the sequences get bigger, unlike KV cache, as I mentioned earlier. So yeah, these models, they can be really efficiently implemented in this recurrent form for like decode steps. And they also had a really efficient convolutional representation for prefill. However, S4 in like the paper in 2021 was shown not to be good at some like downstream tasks, like selectively copying parts of the input and like reasoning about things in the context. So this is where Mamba kind of enters the stage. This is like the first Mamba paper from 2023. This is sometimes called S6 because it adds what we call selective scan, but let's not worry too much about the name. The main kind of innovation of Mamba is that these matrices that I showed you on the previous slide, A, B, and C, they become dependent on the time step. So instead of being kind of fixed matrices for every iteration, they can change. And this was shown to really improve the quality of the model on tasks that involve selective copying or in-context reasoning. However, there wasn't a free lunch here because Mamba 1, it no longer admits this convolutional form that make it really efficient for kind of training or prefilling long sequences. So yeah, in the paper, the authors propose a method for solving this, the selective scan, which is why we go to S6. However, even with that technique, we see that Mamba 1 is still much less efficient than attention-based models. And the primary reason why is that this selective scan algorithm can't use, it doesn't involve matrix multiplication, so it can't use all these tensor cores that we have on modern GPUs. So even if it's super efficient theoretically, if it can only use a fraction of the compute capability that Blackwell or Hopper GPUs provide, we're never going to be, you know, like Flash Attention 3 on realistic scenarios. So that's where kind of the Mamba 2 paper comes in. And the Mamba 2 paper is a really cool paper. It has a lot of, it's a long paper with a lot of kind of insights and ideas. I'm going to cover a few here. Like the first is that you can rewrite this mapping from the input sequence to the output sequence as like a matrix transformation. So you can write a big matrix that maps X to Y, where every, you know, row, every entry in the matrix is some combination of the A, B, and C matrices that I mentioned earlier. These matrices have a very special structure, which is discussed at length in the paper, and kind of how exactly that structure looks like affects how well you can implement this matrix transformation. So the second kind of big contribution of that paper is that they propose a very special structure to this matrix A. Like Mamba 1 used a kind of diagonal matrix for the A. So like you have zeros in the A matrix other than on the diagonal. But in Mamba 2, they go one step further and say this matrix should be like all ones along the diagonal, just multiplied by a single scalar value. And based on this structure, they then were able to derive a matrix multiplication-based algorithm so that can use the tensor cores of the GPU, which can be, you know, get you even better performance than like Flash Attention. So we've implemented this kind of Mamba 2 algorithm in vLLM using a bunch of Triton kernels. And over time, these kernels have been adapted to support, you know, all the kind of critical use cases for vLLM, like tensor parallelism, like chunk prefill, and most recently prefix caching, which is something we're working on right now. Yeah, this figure is from the paper, like which shows the sequence length on the x-axis and the latency on the y-axis, and kind of the purple line is the Mamba 2 algorithm, and blue is like Flash Attention 2. Okay, this was the state of the at that time. You can see here that for long sequences, there's a gap opening up there. Okay, cool. So the final like insight from the Mamba 2 paper, and this is where kind of it connects into Qwen 3 next and linear attention, is that because of this structure, right? I mentioned that the AT matrices is just a scalar times an identity matrix. We can rewrite every element in that matrix, kind of the matrix transformation in this form. So you just have a kind of multiple of scalars times C transpose B. That allows us to rewrite the whole thing, the whole matrix transformation in this form. So we have like Y is equal to C times BT, B transpose, where you apply some lower triangular matrix L, and then you multiply it all by the input X. And if we actually look at the structure of that matrix L, you start to, if you think back to that first slide I showed with attention, you can already see that this L looks very much like the causal attention mark that we apply when we do attention, except we have a kind of more general version of it. And in fact, like this equation is exactly the same as a variant of attention called linear attention, proposed in this paper from 2020, but there's lots of different variants of linear attention, which is basically attention without the softmax in the middle. So you have Q, K transpose multiplied by the causal mask, and then you just multiply it by V without any softmax, which dramatically changes the way you implement this thing. So yeah, if all of these A scalars are set to 1, then Mamba 2 is just exactly the same as linear attention. So that's kind of how these things are all connected. So yeah, as promised, what these are kind of the low-level mechanisms for what are actually hybrid models. It's a fairly big landscape now. This table shows all of the hybrid models that are supported in vLLM v1, and I apologize if I missed anything off here. As you can see, what's common here is that they all use attention. By attention, I mean like full attention here. And then in addition, they use some Mamba or linear attention mechanism as well. So some use Mamba 1, like Jamba. Many use Mamba 2. Then we have some that use variants of Mamba, like the liquid foundation models use something called short conv. Then we have models that use linear attention. So the Minimax AI's model, the Minimax Textile 1, uses a form of linear attention they call lightning attention. And this new model from Qwen 3 Next, uses a variant of linear attention called the gated delta net, which again is very interesting to read about. Finally, you'll notice that some of these models also combine kind of attention layers, linear attention layers with MOE, including the latest Qwen model, as well as the kind of IBM's Granite 4 model, which I'm going to talk a little bit more about when I do the benchmarking. Okay, cool. So yeah, these models are all different. Like, they all use different underlying mechanisms, but they do have some things in common. So in particular, if we think about attention layers from a kind of vLLM perspective, we organize the KV cache in blocks of 16 tokens. Each block corresponds to about, these models are taken the numbers here are taken from NVIDIA Nemotron Nano 12B, again, another recently released hybrid model that uses attention and Mamba 2. So for this model, every block of KV cache comprises around 64 kilobytes. Whereas for the Mamba layer, we have like a single huge state. It's much bigger than a single block's worth of KV cache. It's around 2.57 megabytes. But unlike KV cache, right, we never append to the Mamba state. We always update it in place. So these two things are very different. KV cache, you append or concatenate. The Mamba layers, we like overwrite each time. So, and while the KV cache is much smaller than the Mamba state for a single block, if we look at the KV cache to store a sequence of 128K, it's actually 200 times larger than the Mamba state. So for long sequences, you see how like the state we have to store is significantly smaller. So now let me talk about how these models were supported in v0. As I mentioned, it was kind of a hack. So in v0, we store vLLM has a very efficient way of storing KV cache, right? So we have, for every attention layer, we have a KV cache tensor, and it's kind of organized into blocks where each block consumes like a number of bytes in GPU memory, which we call the page size. So that's this 64 kilobytes that I mentioned. And like a block of KV cache is like the KV cache for all layers in the model, right? So it spans, it's interleaved across all of these KV cache tensors. The Mamba state is not stored in blocks. We simply have a Mamba state tensor for every Mamba layer. And we allocate like one Mamba state for every sequence up to the max number of sequences that the user sets. So this is a big difference. So like for the KV cache, we determine the number of blocks automatically at initialization time by looking at the available GPU memory. Whereas like the Mamba state, which is allocated based on a parameter set by the user. So if the user sets that wrong, if they use the default in like I think 512 in a memory constrained environment, that was often leading to out of memory errors. Yeah, so what's wrong with v0? I mentioned the first thing already. So we kind of burden the user with having to tune this max number of sequences as like to ensure that vLLM doesn't crash. This is a really bad user experience. Like IBM's been building models and people go and try it, and the first thing it does is crash. They come straight to me and say, what's going on? This is broken, blah, blah, blah. So that's kind of one real problem that I was facing daily. So when we try to enable v1, right, we want to unify the management of KV cache in the Mamba state. Like, why do we want to do that? I guess one is just it's more elegant from a code perspective, but the other is that this will eventually allow us to support techniques like prefix caching, KV cache transfer, as well as preflow decode disaggregation. In addition, by porting hybrid models to V1, we can also take advantage of like V1 era features like torch compile, better scheduling, and more. So how did we get it to work in V1? Here I show like how it works for hybrid models that don't involve Mamba. So what does that mean? That means models that, like this example shows the Gemma 3.1b IT from Google. This is a model that doesn't use Mamba, but it's hybrid in the sense that it uses full attention layers and sliding window attention layers. So it has 4 full attention layers and 22 sliding window attention layers. So the way that V1 handles these models is it groups together the layers. So we have 7 KV cache groups here. Each group comprises 4 layers, all of the same type. So either attention or sliding window attention. And then we have to do a bit of padding in some cases if it doesn't perfectly align. And then we create one KV cache tensor for like each element in the group. So in this example, we would have 4 KV cache tensors. And all of the kind of KV cache groups share these KV cache tensors. So we will have like some of the rows like across this structure will correspond to attention blocks. Some of them will correspond to sliding window attention blocks. And what's really important is that in order to simplify the KV cache management, we require that these blocks are interchangeable, right? So that the page size, the physical amount of GPU memory that these blocks consume must be the same across all KV cache groups. This is critical, otherwise we have to do a lot more work in like freeing and figuring out where we can fit stuff in GPU memory once things start getting full. This is a big problem for Mamba because the page sizes of the attention layers and the Mamba layers do not match at all. I'll show an example on the next slide. To solve this problem, we had to relax a constraint that the block size should be the same across all of the KV cache groups. And then we had to automatically increase the attention block size such that it's aligned with the Mamba page size. And I'll show a kind of graphical illustration of this. And finally, we had to reorganize the strides of the Mamba state tensors within the page to make them compatible with how attention is laid out. So yeah, what do I mean about the page alignment? So again, in this example, I show some numbers from Nematron Nano 12B. So this is like inside one of these KV cache tensors. So in the top, we have the like attention layer. So it has a default block size of 16, and the page size is by default like 64 kilobytes. Whereas the Mamba specs, the block size is like the whole sequence length because we never append it. We just have one state for the whole sequence. But the page size is around 2 megabytes, so it's really way bigger. So the first thing that we do is we automatically kind of find the block size that will ensure that the attention page size is bigger than the Mamba page size. And then we pad up the Mamba page size slightly to ensure that these two things are aligned. And you might be saying, wow, that's crazy. Why are you using like a block size of 672 for attention? Doesn't that like kill the performance? Everyone has the same thought when they first see this, but actually we found that this doesn't really seem to make a big difference for these models, perhaps because attention is only a small fraction of like the runtime of these models. Okay, in the interest of time, I'm going to skip these 2 slides because I want to leave a bit of time for questions at the end. So yeah, just to mention some of the other work that was needed to deprecate V0. There was a lot of modeling code change to get this to work. We also had to figure out like how to make it work with different attention backends. Initially, it worked only with Flash Info. Then we got it to work with Flash Attention 2. Yeah, another important thing that you will see in the results is that at least the Mamba 2 layer, I can't speak to all the other linear attention mechanisms. It has a lot of CPU overhead. It has like multiple cores to different Triton kernels. And we see that it's really important to use CUDA graphs for these models. So like initially, we just got it working for eager, but then gradually we've supported like piecewise CUDA graphs, full CUDA graphs for decode-only batches. and most recently, kind of full coup de grace for decode only and piecewise for mixed, which is, I think, now the default. And as I'll show, this has a huge impact on the performance. Finally, like some of the things we're working on now are prefix caching, as well as decoupling this logical block size from the physical page size to kind of solve this problem of having to use a large attention block size. Yeah. Cool, so some benchmarking, then I'll open for questions. So yeah, this is some benchmarks I ran a couple of days ago. So using the latest release of vLLM 0.10.2. This is actually the last version that will support both V0 and V1 for hybrid models. V0 is already not supported for some things, but hybrid models are still supported in V0 in this version. So it makes it ideal for benchmarking these two things. Yeah, it's now gone. So subsequent releases will not have the V0 support. So I just served the model using all default parameters. Then I used the benchmark serving with random data of length 32K input, 128 output. And then I sweep the max concurrency from like 1 to 16 or something. So this is how it looks for Nemotron Nano 12B. The different colors, okay, the different panels show you the time to first token, the ITL, and the throughput. In orange is V0, in green is V1 with piecewise coup de grace, and blue is V1 with full and piecewise. In terms of the TTFT and ITL, V1 is generally better, although there's some cases where it's worse in one and better in the other, and so on. This is probably due to the different scheduling dynamics between V0 and V1. In terms of throughput, it's consistently better, except for very low concurrency, where we see that piecewise coup de grace is actually worse in V1 than V0. Again, this is coming from those CPU overheads in the Mamba mixer layer. So in general, for this model, which is like a dense model, it doesn't use MOE, we see around 2% to 18% improvement in throughput. If we go to a model that does use MOE, like IBM Granite 4 Tiny, which is a 7 billion parameter with 1 billion activated, we see that this effect is even more dramatic, right? So for low concurrency, V1 with piecewise coup de grace is significantly worse than V1. And we really need to use full coup de grace to get better performance. But we see huge gains here, right? So yeah, this is a smaller model than Nemotron 8, but it also is using MOE, so it's more like latency sensitive. We see massive gains from using V1 as well as from using the full coup de grace support. So like in general, we see up to like 91% improvement in throughput, and the ITL and the TTFT is consistently better across all concurrency here. And with that, I open for any short questions you may have in the time remaining.
Yeah, thanks a lot for that overview, Thomas. That was really insightful. There's a question from Adit about the TTFT ITL comparison, maybe
Sure.
specific model. Let's come in which model?
How do I see chat? I don't see it somehow. Wait, here, I got it.
Yeah, to the bottom right.
This command is for which model? Yeah, so like, I just put it with an environment variable because I show results for two, right? I ran the benchmark for this Nemotron Nano 12B, as well as for the Granite Tiny preview. I hope that's clear.
Yeah, I think this question might have been before you actually.
Yeah.
Yeah, any other questions in the chat, or feel free to come off mute. One question I had is that I still don't quite get, that I know we've talked about before, is the prefix caching like plan, like where you kind of ended up there.
Yep. Yeah, like I wanted to cover that too, but I thought we won't have enough time, and I think that was probably the right decision. Maybe we could do a follow-up on that once it lands.
So
yeah, like sure, go ahead.
Yeah, can I ask a follow-up question? So here we are saying that for in TTFT, when we have a high concurrency, V0 is performing better. Yeah, like if you look at the leftmost graph, you can see that.
So yeah, in the ITL, yes, and that's exactly because the Mamba 2 mixer layer has a bunch of CPU overheads, and then like piecewise CUDA graphs, we leave that layer completely out of the CUDA graph. So we CUDA graph everything else, like everything but the attention layer and the Mamba layer. And for attention, that isn't that bad, I think, because like Flash Attention and Flash Info, they're calling like super optimized CUDA libraries. Whereas the Mamba layer is calling like a lot of custom Triton code. It maybe isn't as well optimized as other things. So that's why we see it's like really important for these models. Like actually we didn't
really
sorry,
like I actually don't know this very well. So when is the CUDA code actually called? Is it like when when these models have to run the code on the GPU at that point in time, they call the CUDA code? Is that right?
Yeah, so it's called like at every layer, right? Like every Mamba layer, you have to kind of do a forward pass through the Mamba mixer. You have some like, yeah.
Okay, so at every layer, they will call the, like whenever they need to run some code on the GPU, they will need to call the CUDA code, like either Triton or like whatever kernel that there is.
Yeah, so for like attention, we're normally calling like libraries that are written in CUDA, like Flash Attention and Flash Info, where like everything's compiled ahead of time. Whereas for Mamba and also like the Qwen 3 Next and the Minimax model, it's all written in Triton. So Triton is great, it's much easier to read, but it does have some kind of overheads associated with launching the kernels. But I have to say, I'm not fully convinced that the reason it's so much worse is just because of Triton. I think it may also just be like implemented kind of badly, and we need to go
Makes sense.
fix.
That's okay. Yeah, they might want to ship it quickly, so they just came up with it. Okay, that's okay.
Yeah, like with Triton, kind of the time to get like a working implementation is way faster than CUDA.
Awesome. Great presentation.
Thanks.
Yeah, there's one question on the folder location of newly implemented Triton kernels. There's a lot of them. Usually they're just like local to like wherever we use them for, quantized matrix multiplication. We use them, we have like a Triton attention backend. And yeah, like various like top K like operations like for MOEs and things. Usually it's just like in those specific, like in the same file or in the same directory. There's not a centralized place, but maybe you can say for these Mamba models.
Yeah, like the Mamba models, I think is in like model executor layers, Mamba ops. And then the Qwen 3 Next stuff, I'm not sure where we put it, to be honest. There's a lot of new code that was added there. Like in general, like that's a kind of thing we should discuss in the community. We have like a lot of Triton kernels that we are adding when we, add support for these models, and sometimes we haven't really thought about how we're gonna like maintain that stuff long term.
Yeah, definitely agreed. Yeah, I think for this is like, for instance, for like the Qwen Next, like Flash linear attention, basically everything is like in this dedicated layer ops directory.
Yeah, but also like this code comes from another project, right?
Right.
So
yes. Yeah.
What happens if like bug fixes go in that project, and then you have to manually port everything across? And then what happened with Mamba was we then went and implemented a whole bunch of like vLLM specific optimizations to those kernels. So now that they've diverged a lot from the original kernels that were added.
Yeah, I mean, I feel like it's usually either moved into tree in vLLM, or it's we fork the repo and then maintain our own fork like we have for Flash Attention and Flash MLA, and which it's hard. Other projects have other priorities and people.
I see a question. I heard of Atlas transformer-like architecture from Google. Did you get the chance to find any model with such deep transformers architecture? Going to be totally honest, I haven't heard of that one. Need to check it out. Thanks for the tip. I will have a look.
Yeah, I think I found it. Yeah, I haven't heard of it either. Learning to optimally memorize the context at test time. So seems like it could be related.
Cool. Yeah, I will check it out. Thank you, Shrikant.
Cool. Well, any other questions before we log off at time here? All right. Well, thanks everyone for staying and yeah, being active participants. Thanks, Thomas, a lot for the deep dive into the future of model architectures. Yeah, hope this was insightful and fun for everyone involved. And we'll catch you in the next office hours in 2 weeks.